Okay. Quiet. Okay, today, initially, I will discuss what portions need to be covered, and after that, I will tell you about the exam, just a recap of the portions that we will go through for the exam. Okay. So, so now this carry save adder. Okay, this is a kind of adder which can be used to add multiple numbers, multiple numbers, and each adder works independently. Okay. So a carry save adder is the adder we use in multiplier. That is why I'm talking about it at this point. Okay. So I will discuss multiplier once again. I know there is some confusion regarding multiplier, so I'll just discuss that once again. So we can use a carry save adder to add multiple numbers. Now what happens is that it works independently, means if you remember our full adder, how does a full adder circuit work? I have FA0, FA1, FA2 and so on. If full adders 1, 2, 0, 1, 2, I have inputs coming here. The sum is generated. The carry is propagated to the next stage. Is it not? From FA0, what carry is generated? It will go to FA1. And then same way, this is A0, B0, A1, B1. Then I will get some S1, and what carry comes goes to the next stage. So it is like it is not independent. Each adder block does not work independently. There is a dependency on the previous adder block, is it not? So except for the first one. So when I talk about a carry save adder, I say that it can work independent. It can work independently. Okay, that means there is no interconnection between each adder block. They work separately on their own. So how it does this is that, suppose if I have to add, see, for each block in a carry save adder, what I do is I compute my sum, I compute my carry. So this is carry save adder 0, carry save adder 1. Again, I have a sum coming here. I can call this sum 0, or I don't call it sum 0 because I'm adding three numbers here. Okay, so whatever is generated, I have each of them separately. So there is no connection between the carry of one stage to the next stage in a carry save adder. Okay. So each of them works as independent blocks. Now let's see what the addition looks like. Suppose if I'm adding three numbers x, y, z. Okay, x, y, z is 5-bit long, 1, 0, 0, 1, 1. Yes. हाँ, I will come back to marks because multiplier मैं फिर से explain करूँगी. Okay. So because there was a little bit of confusion there for at least some people. I don't know whether they are all here. Very few students in class. When I'm discussing what I mean, like the topics or the points regarding exam, I will not record it because it is only for people who are attending class. People are not ready to attend class. Why should I share it as a video recording, right? You should have some benefit of coming to class. I told you, clapping. Meet Farmer by mistake is there. I always look for you on the fourth row. You say you're always sitting in the fourth row. Okay. So, okay. So I told you, clapping is not enough. Still, you're not listening. No chocolates have come till now. Okay. So 1 1 0 0 1 0 1 0 1 1. Yes. Okay, so now if I'm going to add this, on one side I find the sum. Okay, sum means when I add, I ignore the carry. Okay, when I'm finding the sum, I ignore the carry completely. So here 1 plus 1 plus 1 will give me 1 1, right? That means sum is 1, carry is 1. But I don't take the carry into consideration. I'm only concerned about what is the sum generated. Okay, so then next one, 1 plus 1 gives me 1 0. So 0 is the, okay, 0 is the sum. 0 plus 0 plus 0, 0 is the sum. 1 plus 1, it's 1 0. So 1 is a carry, 0 is the sum. 1 plus 1, again 0 is the sum. Okay. No carry. I'm not adding the carry to the next succeeding bit position. Now, same way, I'm going to write, I'm going to find the carry also. So now carry. So 1 plus 1 plus 1, 1, 1 is the sum. That means carry is 1. 1 plus 1, 1, 0 is the sum. So carry is 1. Next 0 plus 0 plus 0, 0. 1 plus 1 plus 1, 1, 0 is the answer. So carry is 1. Sorry, carry is 1. Carry is 1. And 1 plus 1 again, I have carry 1. So I get carry as 1, 1. Oh, here it is 0. Just 1, 1, 0, 1, 1 as a carry. Okay. So sum is computed separately, carry is computed separately for the bits I'm adding. Then what I do is in another stage, I can add the sum and carry with appropriate shifting. What do I mean by appropriate shifting? If I'm going to add the sum and the carry, I have to add what sum I have got here and the carry I have got here, because in the first case I have not considered the carry. That does not give me the final sum. Yes or no? So now if I'm going to add sum and carry, I have to do shifting. I say, why do I have to do shifting? Carry. How carry is generated? Dekho, X, Y, Z, if I go from the LSB, 1 plus 1 plus 1. What is the answer? 1 plus 1 plus 1 gives me 1, 1. So carry, this is carry. So I wrote the carry here. Okay. Next stage I'm adding 1 plus 0 plus 1. The answer is 1, 0. Carry is 1. I wrote it there. Okay. That is the way we write. Okay. So now I have to add these to what I have got separately. Now when I add it this way. Is this correct? Why? Why do I have to shift my carry to add? Yeah, because in the LSB position there is no carry generated usually. Usually no, always. We don't have a carry in the LSB position when I add. Right? There is no incoming carry there. So carry, whatever is generated, has to start from the position next to the LSB. That is why we shift the carry and we add finally. Okay. Compute sum separately, compute carry separately, and in this way, so this answer comes to 1, 1, 1, 0, 1, 1. Okay. So this is your final answer. Sum plus carry, whatever it is. Okay. So it's 5 bit 1, 2, 3, 4, 5. So this is your final carry. C out is this, and this is your sum. 5-bit sum plus 1-bit carry. Okay. Now, here, if I can add as many numbers as I want and generate separate sum and carry, and then I can go on, I can go to a next stage and uh, add them all together. Okay. So, how the circuit looks like is that I have, so in one carry save adder, I can have three inputs. As you saw, X, Y, Z, we were adding. So, three I can do. Okay. So, this generates a sum and a carry. Now, in order to combine this, I have to use a proper adder, like your full adder circuit. What do I call that? It has a name. It's called a ripple carry adder. Remember, I have mentioned this ripple carry adder. Why do we call it a ripple carry adder? Because the carry is rippling through the stages. From the previous stage, it ripples to the next stage, and so on, right? Carry moves through the stages. So we call it a ripple carry adder. Finally, to do the final stage of addition, I need to have this, I have to give to a ripple carry adder to do the adjustments and get as it is. Okay. Now for three numbers, I'm saying this. Now suppose if I have six numbers to add, okay. How does the circuit look? No, first four numbers, let's say four numbers. So, so the numbers M is the number of inputs I have. Okay, so here M is 3 and this is my circuit. Now M is 4 means this is my first carry save adder. Three numbers are added. Then I have sum. Then I have separate carry that comes in. And this I have my fourth number. Okay, whatever it is. Suppose if I call my numbers x1, x or okay, x, p, q, r, and s. They are my numbers. So, okay. So then S I can't call. Let's call it T because already sum is there. So call it T. So by numbers are P, Q, R, and T. Okay, these are the numbers to be added. Okay. So in the next stage, what will I have? I will have now again I have three inputs. So I can have a carry, save adder again. Now when I add these three, I get a sum and I get a carry, which is independent, which is so then I have to again have a normal adder. I have a ripple carry adder here. So always in this carry save adder, the last stage will always be a ripple carry adder. Okay. So I can add three bits independently, go on adding depending on how large my circuit is. But in the final stage that I will have a ripple carry adder. Okay. And sum. Now, if it is 6 bits, 6 bits, if m is equal to 6, see, I have three inputs here. I can have another one here, which also takes in three inputs, generates a sum and a carry. It also generates a sum and a carry. So I can have another this here. I can give this also here. So now I get again some carry. If I have one more here, this also can be given here. Yes or no? So so now everything has been added. All the sum carry generated from different blocks have been added. So now I need to finally get the answer. So I have a ripple carry added. So I have C out and sum. Okay. So you see that carry in, see the carry, what we have to observe here is that the sum or the carry generated here is used in a stage which is like, this is called stage one. Okay, first stage, second, this is third. So this carry generated here was used in the stage three. So in some subsequent stage, I will use it. And finally, I normalize everything using a ripple carry adder to get the proper output. Okay. The use of this, what could be used if I'm using a carry save adder? As you say, why should I use it? I can just use a ripple carry adder. What could be an advantage of using this? Can you think of any advantage? I'm adding six numbers here. What could be an advantage here? No, nobody knows. Suppose I'm doing this parallelly. I'm doing this addition and this addition in one go. Same time I can do it. I can save on time. More addition can happen. In ripple carry adder, I have to wait from A0, B0 to go to A1, B1. Yes or no? Because this carry has to come. Then only I can do the next addition. Here I don't have to wait for that. The first three numbers are added here. The next three numbers are added here separately. The sum and carry are separate. So the first stage can happen on its own. So that is why we will be able to reduce time if we use this adder. And this adder finds application largely in multipliers or in pipelining. Okay. So we will look into that. Is why I explained this before coming to the multipliers. Okay. Now, is that clear? I hope it is clear. Okay. Now, multiplier, I'm not going into 4 by 4 multiplier. You need not draw the circuit also, which I'm showing now. It is just to explain the concept to you because you have already drawn. I mean, those of who drew, it is there. Otherwise, it's there in the previous video lecture. So here, if I'm going to multiply, so 3-bit means it's A2, A1, A0 and B2, B1, B0. So I get A0, B0, A1, B0, A2, B0, then I get A0, B1, A1, B1, A2, B1, then A1, I mean A0, B2, A1, B2, and A2, B2. Okay. So what do I call each of these terms? A0, B0, A1, B0. What are they called? They are called partial products. Okay, partial products. Now here, so what I get, these places I have zero basically, right? Nothing is added there, it's zero. So this is called P0. This will be P1, P2, P3, P4. Now here, so if I want to generate each of these things, the partial products, how do I generate the partial products? All these product terms I generate using, because it's a product term, I use which gate? I have to use an AND gate, right? So I have an AND gate. So A0 and B0 is given as input. I get A0, B0. If I give A1 and B0, I get A1, B0. So in this way, all these terms, all the terms that I have written here as a partial products can be generated in one go. The same time, simultaneously, I can generate all these product terms. Now, so now if I'm going to write what, so the first product, okay, first product is going to be just an AND gate. P0 is generated by this AND gate itself. There is no addition happening there for the LSB. This P0, it's A0, B0 plus 0 plus 0. 0 and 0 I don't need to add because it does not make any change to my number. So directly I get P0. Okay. Now, now look at this stage of addition. Okay. So this I don't even need to write the zeros because I know there is nothing I have to do there. Okay. Now to here, in this stage, will there be any carry coming in from P0? No carry will come in. Why? Because it's just an AND operation. There is no addition happening there, right? So there is no carry coming in. That means I only have to add the numbers A1, B0 and A0, B1 to get P1, right? This will generate P1. Yes or no? If I add those two, I should get P1. Now, so there is no carry coming in. So do I need a full adder here to implement that? Full adder means I can have three inputs. One C in is also my input, no? So I don't need. I can implement it using a half adder. So half adder saves space also, time also. It's faster. So I use one block which I call half adder, and I give the inputs. One is A1 B0. The next one is A0 B1. Okay. Now, if I have a half adder, definitely when I add, I will have a sum and I will also have a carry, right? Now, this carry, now this carry, see, I can, now this carry has to go here. I call that carry C1 because it is generated from the addition of these two bits, I mean, products which generate P1. What carry comes, I call it C1. Okay, so let C1 be here. C1 has to be added in this column. Yes or no? This has to be added in this column, right? So my to get my P2, I have to add A2 B0, A1 B1, A0 B2, and C1. Okay, whatever it is. Then only I will get my P2. Now, so I can give this carry here, and then I can use a full adder here. Okay, I can use a full adder here, and then what inputs? One input is a C, which is coming from this, which I can call C1. So that comes in, and I might two other inputs. That is the first two product terms I can give as the other input. So I have A2 B0 and A1 B0. Okay, so that will generate a sum and a carry. Now, I am not going for this design. Why I am not going for this design is because, see, is it significant whether I add carry with these two or whether I add carry with this one? I mean, anyway, I will have two stages of addition here. Okay, because two bit combinations, even if it is three, if I add these three, then I mean, I have to have one more stage of addition, right? So is it important that I should add the carry only when I'm adding the first two product terms and partial products? It's not necessary like that. I can add it anywhere. I have the flexibility to choose whether I wanted to want to add it with the first two partial product terms, A2 B0 and A1 B0. I mean, A1 B1, no? Yeah. Okay, so A1 B1, or later with A0 B2 and the sum which is generated from here. Okay. And when I use, so I am not going to use a full adder here because I can, if I'm going to add only without the carry, I have only two inputs that I'm considering, right? Which two inputs? these two. I'm not taking C1 now. C1 has to be added when I'm adding in this row, I mean in this column, but it can be added later also. There is a flexibility to add it later. So I am thinking I will add only the first two partial product terms. So if I have to add only two partial product terms, what can I use? Half adder again. And when I use, so that means this carry is also not coming for me, right? There is, like, I'm not going to use a carry because it is a half adder. So there is a carry generated, but I'm not using it in this addition. And when I use a half adder here, one thing is that the structure becomes modular. That is, like, in one row I have half adders, maybe in the next row I will have full adders, and so on. So larger the multiplier, it will give you a more modular structure or a regular structure. Okay. So to make the structure modular, I decide to use a half adder in the first stage. So now when I'm going to use a half adder here, now the inputs are A2, B0 and A1, B1. Okay. So now when I add it, there is a sum generated. There is also a carry generated. Okay. Now this sum, now here, so what all comes in now? Next stage of addition. This is not complete. I have to do more addition. So by adding these two, I get a partial sum. Right. When I add A2 B0 plus A1 B1, what I get is sum. I call it a partial sum. So when a sum is produced, I could also have a carry generated there. Right. When I have a sum, there is also a carry. In any addition process, I have sum and carry. So, so that is what, when I added them, I got in the half adder, I got a sum and a carry. Now sum I have passed on to the next stage. Now is this over? How many things do I need to add? Okay, the carry I have taken here. This is C1. Like what I have written here, it is C1 which is coming from this half adder. So now I have taken care of the carry. I have taken care of this partial sum. And I have this one more term. Yes or no? Right. So that also needs to be added as an input. So here I can add that term also. So that is A0, B2. Now what is it? I have three inputs. So what does it become? It becomes a full adder. Okay. Yes. So now is my addition complete? Have I added all the terms? Here I added the first two terms. The sum was, partial sum was generated. I added the carry from the previous stage. Okay, I adjusted the carry here. I also have one more partial product term, that also I put in here. So now my addition is complete. Okay, and P2 is generated. This was P1, huh? I didn't know. So P2 is generated. Now, so when this addition happens, this is the sum. Again, I have a carry. This carry. So now, how many carries can be generated from this stage? When I have two additions happening, each stage generates a carry. Yes or no? It can generate, it cannot generate. So both possibilities are there. So there can be a carry. So that is why from this particular stage, okay, this particular stage, I have two carries coming. Okay, which I need to appropriately add in the next stage. So what is my next stage? I have only this. So I can say I have C2A and C2B coming in. Because if I call this C2A and C2B, okay, two carries are coming in from two stages of addition. Now here, now only if this carry comes in will I be able to do the next addition. Because I have to adjust. Here you see, I have how many numbers in the next stage to add? I have only two partial products to add. Okay. So I have A2 B1 and A1 B2, and I also have C2A and C2B. Yes or no? Yes. So here I come. So now if I have to add these, I can add these three. Why? Because earlier I used a full adder. At that same level, I can have another full adder, regular structure. Okay. So here I have one C2A as the input, A2 B1 and A1 B2. Three inputs have come, sum is generated, and then carry is also generated. So here the sum. Now what all comes in? I have to also add with that sum, partial sum, I have to add C2B also. Yes or no? So now there are only two inputs. So what should I add? Use there half adder. So this generates a sum, and that is my P3. And then this will also generate a carry. Okay. Now this has to go to the next stage. So next stage will have this carry coming in. Yes, whatever has come from. Now what is the last stage? I'll write it first so you can know. The last stage, if you look here, my last stage is just this. Okay. Okay. Now, since in the previous stage I had a full adder and a half adder which I used, I will have two carries coming in. Let me call it C3A and C3B. Okay. So I have to somehow adjust it here. Okay. So now I have only one number, but I have only A2, B2. Right. A2, B2. So here I have a full adder, and that takes A2, B2. The carry, this is C3A, and this is C3B. So all these carries it takes, and then I generate the sum which is P4. Okay, and now after this operation there can be a carry. That carry will be my P5. Okay, P5. I don't know whether you can see till there. So this is already there in the 4 by 4 multiplier circuit also. If you see, it is done neatly. Now here you can see that in this last stage, this half adder, okay, where I have used this half adder and full adder, from the half adder, the carry is not propagating to any lower stage. It is not going below, right? Is it going below? No. I have added it directly parallelly to this. Okay. Not parallelly, in fact, serially. From this, when this carry is generated only, this addition can happen. So this carry needs to be generated so that this happens. So this part becomes a ripple carry adder. Remember the carry save adder that I mentioned. So all those things that we did were we were propagating the carry to the next stages. Yes or no? Everywhere this is going to next stage here. This is going to this stage. So everywhere it is happening the same way. This is going to this stage. It's going to a next level. But in the last stage, I have to accommodate all the sum and carry finally to generate the proper output. So this happens like a serial adder. That is from one to the other. So unless this half adder output is available, I cannot do this full adder operation. Okay. Now, that means if I have, now let me take row by row. Okay, this is row 1. In row 1, can I do all these operations parallelly or not? Can I do them separately? Yes, I can do them separately because none of them is depending on a previous stage. Right, there is no carry incoming, there is no connecting lines between them. Okay, no input coming from this half adder to this. So, but if I look, so same way, if I look at this stage, row 2, row 2, what about this stage? This row also, each of the full adders are working independently because they are only, when this has to work depending on the carry propagating from the previous row. Yes or no? The carry for this full adder comes from, if I call this H1, H2, F1, F2. So this also again 3 and this is 3. Okay. So in that case, if F1 has to work, if I have to get an output from F1, I need the carry from H1, which is in the previous row. Okay. Nothing in the same row. Right. So in the same row, they all work independently. And this will be generated by the time we reach the next stage. Okay, so I can reduce the delay here. So now if I have to get how much time do I take to generate the product of a multiplier, how do I compute it? Do I have to take, okay, this half adder time, this half adder time, plus this this full adder, this full adder? Do I need to take that? Or in every row I can consider only one because each of them work parallelly. So here I have to take, okay, the time taken by a half adder, okay, the delay of a half adder. In this stage I can take it is a delay of a full adder. Here when I come, now this becomes a ripple carry adder. Okay, because there is serial connection from this to this. So that means here I have to take all the component bits. Okay, in the final stage alone, you will have to consider the delay of every component connected because it does not work simultaneously. It works in a serial fashion here. Okay, so And here I will have the delay of the half adder plus the delay of the full adder. Okay. So that is what I have already mentioned it as propagation delay, critical path delay in your multiplier. You have written it. I was just clarifying it a little more. So, okay. So if I'm going to say the propagation delay, so propagation delay would be, so first stage I have T of a half adder plus second stage I have T full adder. Next stage again I have a half adder plus full adder. And all this works when I have my partial products generated, right? If partial products are available, only the rest of the process happens. Addition happens after partial product generation. That means that will include the delay of an AND gate. Okay, because that happens simultaneously. All products are generated at the same time. So I have to consider the delay of a single AND gate for that. Is that clear? Okay. So now this becomes T AND plus how many half adders? Two are there. So two and two full adders. Okay. Okay, this is the total propagation delay time. Now this keeps varying when this is a 3 by 3 multiplier that I have drawn here. When you have a 4 by 4, this is not going to be same. Those who have written down, can you just go back and check what I have written for propagation delay for 4 by 4? No, before that. I mean, this is in number form I have written, no? So this part, if you see, is the same. Yes or no? This much part is the same, whichever multiplier I go into, but the number of full adders changes there. Okay. So that is why we write it as a generalized equation. We wrote that T and plus 2T half adder plus 2n minus 4 time of full adder. Now, if it is a 3 by 3 multiplier, if 3 by 3 multiplier means my n is equal to 3. Okay. In that case, what does this become? This becomes T and plus 2T half adder. And this becomes 2 3s are 6 minus 2, 2T full adder. Right. Now, if I'm having 4 by 4 multiplier, this changes to T and plus 2T half adder. Now, this is 2n means 4 2s are 8 minus 4, 4 full adder. Time for 4 full adders. Okay, that's why this becomes a generalized formula for computing the propagation delay or the time taken to do the entire process of multiplication. Okay, yes, this will, that's it. I am doing this process of multiplication. For doing multiplication, I need these as my inputs, no? All these partial product terms. How do I generate partial product terms? I have shown here, no, here only I had shown, I think, earlier. So I have to write A0, B0. I give it to an AND gate, then that is generated. Same time, I can give A0, B1 to another AND gate. So all parallelly, I can generate it at one time. So that the delay of a single adder, I mean AND gate also needs to be added because to generate the partial product. Okay. So this is how we compute the thing. Okay. And how many adders are there? So if I go back previous page, how many adders did we have in total? We had 1, 2, 3, 4, 5, 6. 3 half adders and 3 full adders. Yes or no? Here. Okay. So I have 3 half adders, 3 full adders. So this is 6. This I can call it as n into n minus 1 adders altogether, total adders. Okay. Total number of adders. Okay. Does it work? Here it works because if n is 3 means 3 into 2, I get 6. So that is the total number of full adders that I mean, total number of adders that I have here. In your previous 4 by 4 circuit, we had 12 adders. Okay. So there it is, n is 4. 4 into 3 gives me 12, n into n minus 1. So this is the standard equation which gives me, or the formula which gives me what is the total number of adders in any multiplier. All right. Is multiplier a little clear now? Okay. So now we'll come back to multiplexers. So multiplexer, we already discussed what a multiplexer does. You know that it has many input lines, which from one of the input lines, data can be connected to the output line, a single output line we have. Now for exam and all, when you're drawing a multiplexer, we want you to use, suppose if I have a 2 is to 1 mux, I have two input lines, maybe I call it I0 and I1. I have to specify whether it is connected to 0 or 1. Okay, because the select line accordingly selects the input, right? I cannot just not mention 0 and 1 here. So this is very important when you're drawing a multiplexer. This is my select line. So this, so what is it going to be when select is equal to 0? My input corresponding to that binary position 0, okay, or the input point 0 is connected. So when S is 0, Y is equal to I0. Yes? Yes or no? Marks you already did in lab also. Now S equal to 1 means Y is equal to I1. Okay. So, I can write the equation for Y as S bar I0, because when S is 0, the output will be I0. If S is 1, my output will be I1. So this is the equation for that. So either this or this. Okay. So select line plays an important role. And if I have M select lines, I can have 2 raised to n m input lines. Okay. That is how it goes. Okay. So we saw marks and we said that if I can, uh, instead of using the gate wise implementation, here I have AND gate and I have OR gate also. So I need to have two ICs. I was mentioning about the number of ICs I require. So because and OR functionality will not come on a single integrated circuit chip. So when we are using it, we need to go for multiple chips. Instead of this kind of an implementation, even for other circuits like adders or any function, Boolean expressions, if I'm able to use a multiplexer to realize it, maybe the circuit will be more simpler. Okay, so I can reduce the number of gates I use. So let's see how we do that. That's why I was saying we were discussing about 1-bit full adder circuit for that. So realization. Okay. So once again, I know you have written the truth table. Those who have written, you don't have to write. For a full adder, I'm writing the truth table. Okay, I'm just writing some for the time being. Okay. Now, if I say I want to use a mux to implement this circuit, that means mux means, I should have some select lines, no? I have to use select lines to implement this. So, and now how many input combinations are there? There are a total of 8 input combinations. Okay. Now here what I'm going to do is I'm going to use A and B as my select lines. Okay. I always use the most significant as my select lines. If I want to convert any kind of a logical circuit or I want to represent it, realize it using a multiplexer, then I take the most significant bits and use them as the selector inputs. So if A and B are the selector inputs, let's see the combinations. What all combinations can A take, A B take? Four combinations. Yes or no? Bit combination 0, 0, 0, 1, 1, 0, and 1, 1. Only four combinations my select lines can take. So this becomes my select lines. I can write it as S1, S0 because I am modifying it as select lines. Okay. Now when A and B are 0, 0, which are the cases? These two, no? Yes or no? So if A and B is 0, 0, what is my sum? Now these two I don't have to look at because they are the select lines. Now I have only one input in that case. What is it? C in, right? A and B. So when C in is 0, my sum is 0. When C in is 1, my sum is 1. That means my sum will be C in when my select input combination is 0, 0. Is it clear? That part how I explained, is it clear? So select inputs can take four combinations 0, 0, 0, 1, 1, 0, and 1, 1 because two bits for select inputs. And if A and B are 0, 0 because they have now been converted to my select inputs, when AB is 0, 0, I have two cases to consider, this case and this case. In these two cases, the sum is now dependent on C in alone. And what is the dependency? When C in is 0, the sum is the same as C in. When C in is 1, the sum is 1, which is C in itself. So in this case, when select lines are 0, 0, my sum is going to be C in. Next case is when select lines are 1, 0. No, 0, 1. Okay, 0, 1. 0, 1, what happens? C in bar, is it not? When both are, I see when C in is 0, my sum is 1. So there is, and when C in is 1, sum is 0. So I can call that this is, you can say sum is C in bar in this case. Okay, this is for this is for this. Next, 1, 0, what happens? C in bar, right? And the last case, C in. Okay, so this is what, now I'm going to draw my multiplexer. So my multiplexer has two select lines. That means how many inputs? Four inputs, right? Two select lines means 2 to the power 2 inputs will be there. M select lines, 2 raised to m inputs. So my select lines S1, S0, I give A and B. My input 0, 1, 2, 3. What is the first input? 0, 0 means C in. Next one, it is C in bar. Next one also C in bar. Last one is C in. And I get my output. I don't get Y, I get my sum as my output. Sum is my output. Yes. Similarly, we have to find for carry also. I just drew the part for the sum. So sum itself, now the circuit has become very simple. There is not much of things there. I mean, the input side, I have used A and B as my selector bits. So I have to only have the complement, one inverter to invert my C in at the necessary places. Okay. So I don't have any additional AND or gates. Okay, here. Now, so now let's see about the carry. Okay, have you drawn this thing? Even if you have to write 4:1 marks and all, okay, all these things needs to be written inside. When you're writing a complete, the box should not be empty. What is the box you have to write? Whether it is 2:1, 4:1, whatever has to be mentioned. Only then your representation, schematic representation is complete. Inputs, outputs, selector pins, then input position 0, 1, 2, 3. Correspondingly, everything you have to mark. Okay, then only it becomes complete. So now, is it done? I'm going to rub this marks for the time being. Okay, because I have to write what the carry is now. So carry now. So little more. I will take another color now. Again. So my select, this is for sum. Now I'm going to write the same thing for carry. My select bits are the same. When select bits are 0, 0, this is the block that I consider. What happens to my carry? When select bit is 0, when carry in is 0 also, my carry out is 0. I mean, carry out is 0, right? When this is 0, this is 0. When this is 1, then also it is 0. So is it actually depending on my C in? No, it is always going to be 0 only in that case. So that means my C out is going to be 0. Okay, that input should be, pin should be 0 because it is not dependent on my carry in this particular select condition. Yes or no? Okay, why? Because in one case, when carry in is 0, my C out is 0. The next case, carry in is 1, still my C out is 0. So it is not dependent on C in at all in this case. Next case, what happens? What is the condition here? C in is 0, C out is 0. C in is 1, C out is 1. So this becomes C in. Okay, when 0, 1 is a combination, it becomes C in. This way you will have to write, because we will give you any kind of, we can give you any kind of function and tell, try to implement it using mux. Okay. So why I am explaining this way is so that you understand how you realize the function, because you will use the most significant bits as a selector bits. Then your circuit becomes a function of only what is remaining. Now AB was used, the other input remaining was C in. That is why all the terms are in terms of either in terms of C in or 0 or whatever. Okay. Next case, 1 0, what happens? What is the function? When C in. And last case, yeah, it is not dependent on C in, because in both cases the output is 1. So 1. Okay. So now this I can again draw a mux. 0 1 2 3. I have my selector which says 1 S0, and I have C out as my output. So here what comes in? The first input 0 0 condition, it is 0. Next one, it is C in. Again C in. Last one, 1. Is it clear? Yes or no? Yes? Okay. So now I get a mux. Okay, so I saw how I can generate my sum and carry using 4 is to 1 mux, right? This is 4 is to 1 mux. Now I get an IC which is called a dual 4 is to 1 mux. That means within that IC, I can have 2 muxes. Okay, 2 4 is to 1 mux. So that becomes convenient for me. That means using this, I can implement my full adder. Yes or no? 1 bit full adder will come. 1 mux for sum and 1 mux for carry. Okay. So here, so what is this? This is for sum I'm taking. Okay. This is why this is sum. Now here, what was the previous? If I see, it is C in, then the next two are C bar, C in bar, and then last one is again C in. So this is C in means this goes to 2. So the last one also, it is C in. I invert this, I can apply it to this, becomes C in bar. It goes to these two. Okay. Yes or no? Okay. And next case again 0, 1, 2, 3. C out. So I have S1 as 0. That is A and B. Now if I see the previous thing, in this case it is 0, C in 1. Okay. So 0 means what? What do I mean by 0? 0 volts means what is a, where do I connect it to 0? 0 means ground, right? Ground. Ground and VCC. You learned op amp, right? So we have ground and VCC. So this 0 means it is ground. Okay. And then these two are C in. So C in I can give together. Okay. And the last one is 1. So that can be your VCC, whatever voltage corresponding to the IC's VCC. Okay. 3 volts, maybe 5 volts. So depending on the IC supply voltage. So in this way, I got a very neat circuit. No additional gates, nothing. And I'm using only C in and C in complement. So using a single inverter additionally, I'm able to implement this circuit. Okay, using a dual 4 is to 1 mux. Okay. So I can save up on space of having additional ICs. I told you, and IC is separate or IC is separate. Then there is a limitation on the number of gates within a specific IC. If it's two input, I can have four gates. Otherwise, I can have three gates. So I have those limitations. So as the circuit gets larger, I might have to clutter up a lot of ICs. If I use a mux, I can significantly reduce this. Okay. So for a larger circuit implementation, it will be very useful. Okay. This is a simple circuit that we are seeing to see how we realize it. Okay. Now, now let's implement another function. Okay, so this is clear. Okay, I'm going the next thing. So okay, so I have a minterm given to me for the function representation. So I'm going to draw the K map here. Actually, in the previous question, also last class when I was teaching, I started with the K map. I drew the K map, but I felt it would be a little more confusing for you people. That is why I directly took from the truth table. But you can do either ways. Okay, you can observe the truth table and figure it out, or you can do this and figure it out. Okay. Similarly, when you're writing K maps, the variables should be written on this line. I see in lab people writing variable names, forget it, and after that, the 00011110. These things should be marked. Okay, so don't omit these things and come up with some equations and all. You will lose marks. Okay, if we are asking for those things. So okay, which all cases when it is 1, then 4, 5, 7, 8, 9. Okay. Okay, so now what I'm going to implement it using is, see, this is to be implemented using 4 to 1 mux. Okay, this is to be implemented using, I'm going to implement this function using a 4 is to 1 mux. Okay, so so 4 is to 1 mux means how many select lines will I have? 2. So that means according to this, A and B will be my select lines. I told you I will take the MSB two things as my select lines. So A and B are going to be my select lines. Okay. Okay. So that means all my inputs will be function of what all? Of the remaining two inputs. What are the remaining? So it's going to be a function of C and D only now. Okay. My input, whatever I'm going to compute and write over. So now, so the first case is when AB is equal to 0, 0. Okay, right. Select. I'm writing the select line combinations. I have 4 combinations for my select line: 0, 0, 0, 1, 1, 0, and 1, 1. Now, when AB is equal to 0, 0, which row should I look at? The first row, right? Here I have only one case where the value is true. What is that? When C is 0 and D is 1. So I can write it as the output F is equal to C bar D. Okay. Now next row, when I come to the next row because 0, 1 is my next combination of select lines, I have to come to the next row. So I come here, I have 3 cases where it is true. Okay. So I'm going to write it over here. The 3 cases means the first one is when C and D are 0, 0, right? 0, 0. So C bar D bar plus next case is when it is C bar D. Last one is CD. Yes or no? So now let me combine these first two terms. I can write C bar, D bar plus D plus CD. So this becomes 1. So now C bar plus CD, what is that? C bar plus D by absorption law, right? So this is what I have to write here. Got it? I simplified it. C bar plus D. Actually, looking at the truth table also, you can say this. How you say this from the truth table is that if you look at these two cases, what is the value of C? In these two, I mean the first two columns, what is not changing? C is not changing, and C is C bar. So C bar. And if I look in the next two, what is not changing? D. And D is having a value of 1. So C bar plus D. Either when C is 0 or when D is 1, whichever case, in all those cases, you can get it. So if that is confusing for you to decipher from the K map, you can do this way. Okay. So that's why C bar plus D I got by simplifying it. Now, what is the third case? Yeah, this is C bar, I can say. Okay, what is not changing is C bar, so C bar. And the last one, no, that is not C bar. It is 1 0 is over here, right? 1 0 is the last one. So that is, this is 1 0. So there I have C bar D. And this 1 1 becomes C bar because C bar is one that is not changing. Okay. So now it's become very simple. I have the mux. I need to have additional one AND gate and one OR gate. Is it not? And one inverter. I will have one AND, one OR, and one not. Okay. If I have to do it additionally. Because I have C bar dot D, I have C bar plus D or D. So, and I have C bar. So these three gates I will require additionally. So 0, 1, 2, 3. First one is C bar D. Okay. So you just write it. And we are not actually making the connections or anything. C bar plus D, C bar D, and C bar. S1, S0, I have A and B. And my output Y will be F. Okay. So as you can see, I mentioned first itself that when we take A and B as the select lines, I have taken because it's a 4 to 1 mux, I have to take the select lines as AB. Now here I have to use, yeah, C and D only will be the other inputs which are going to govern my outputs, right? So there you can see that it is, all of them are C and D, functions of C and D only, either C or C and D. Yes or no? As I told initially, all those things are okay. Now, so, okay, let's look at something called mux trees. Now see mux, I have small mux, like I have 2 is to 1 mux, 4 is to 1 mux, even 8 is to 1 mux is available, possibly 16 is to 1 sometimes. But if I want to make larger mux, 32 is to 1, 64 is to 1, these are not available as ICs in the market. Okay. So what I have to do is that I have to construct these larger or muxes of larger complexity from muxes of lower order. Okay. So, so mux trees are used to construct muxes of larger complexity from smaller mux. Okay, from smaller muxes I can construct them. Okay, so that means if I want to construct a 4 is to 1 mux using only 2 is to 1 mux. Okay, if I'm going to construct a 4 is to 1 mux using only 2 is to 1 mux. Okay, so what happens? So I have 2 is to 1 mux. This can take only 2 inputs. 4 is to 1 means I will have a total of 4 inputs, right? So how many 2 is to 1 mux do I need? If I have to take in 4 inputs, I need to have 2 of them. So this takes in the input 0, I0, I1. Similarly, I have another 2 is to 1 mux, which takes the input I2 and I3. Okay. Okay. So, and then now each mux has one output, right? So I call it Y1 and I call this Y2. But I want a 4 is to 1 mux means I should have only one output. So what do? I should have one more 2 is to 1 mux. So now I have only one output y, right? So using two stages, so this is what I call a mux tree, because in different stages I am implementing it. Okay. So now the same way I can implement my 1-bit full adder using 2:1 mux trees. Okay. Huh? Here, no, that will come. Here I'm just saying the structure. There will be 2:1 means there will be only a single select line. We are not designing anything now. No, I'm just saying that it is a 4:1 mux. So I have not mentioned about this is what the structure will look like. I am just telling you the structure. We will do a question, then you will know what are the select lines. Okay, there will be select line because 2:1 means single select line will be there. Now, whatever the select line is, in each stage will be operated with the same select line. Suppose if I have A and B, which I can use as select lines. Suppose, okay, I'm just saying an example. If A is the most significant, it will be in the stage closest to, this will be the select line for the stage closest to the output. Okay, the most significant one, if A is the most significant one, then it will be connected to as the select line of the mux, which is in the stage closest to the output. Next, I have B also, which I can use as a select line. That will be used in this stage. Got it? Okay. So in every stage, it will be the same select lines that I use. If I have multiple, if I have four, 2:1 muxes in this row, suppose if I had four, okay, then each of them will still have B as a select line. Okay, they have a common select line. Is it clear, Jay? Okay. Now, so implementing, I'll just finish this 4-bit full adder and I'll stop. 1 bit, I mean not 4 bit, 1-bit full adder using 2:1 mux. Okay, mux trees. So if you go back to our previous page and see in our, I needed a 4:1 mux, right? This is with my circuit for, not this one, previous one. Yeah, here each of them was a 4:1 mux for sum and carry, right? So here also, actually, I need to have 4 input lines if I have to generate my sum and carry. So I have a 2:1 mux that can take 2 inputs. I should have one more 2:1 mux which can take 2 inputs. The same thing as I drew before. Okay, this is converting my 4:1 mux, which is actually required for implementing a full adder, and I am implementing it using 2:1 mux. Now, so here, in that case, which all were the bits? I had my inputs as A, B, and C in, and I used A and B as my select lines. Yes or no? Right. I use A and B as my select lines. Now I said A is the most significant, means it is going to drive the select line of this stage. Okay. This is going to be my, let's say, sum. I'm finding sum. So here again, this will be driven by, the select line will be driven by B. It is the actual inputs of the circuit that I convert to select inputs. So I will take the MSB as the select line for the stage closest to the output, and the one before that will have the other one. Okay, is that also clear? Okay, now what should be the inputs? Now suppose if my cases are AB is equal to 0 0, if I can write it from AB is equal to 0 0, yeah, AB is equal to 0 0, I had C bar B, I think, no, C in. Okay, let's say AB is equal to 0 0, my sum was C in. 0 1, my sum was C in bars, 1 0 was C in bar, and 1 1 was C in. Okay, this I have with me. Now this should generate the sum similar to that, right? So if A is 0, I'll use another. So if A is 0 and B is 0, B is 0. Okay. Now when A is 0, which input will be selected for this one? This one, right? Whatever this input is. Now, this input comes from where? From this multiplexer, yes or no? Now B is equal to 0 means which input will be selected for this top multiplexer? The first one. So I should have my C in here, right? Only then C in will come to sum when my select bits are 0, 0. Yes or no? Now if I am saying my select bit is A is 0, B is 1. So if B is 1 now, okay, the rest is all the same. B is 1 now. In this case, when B is 1, what happens? Again, A is 0 means this is the one selected, this path is selected. So it comes here. But B is 1. That means in the top multiplexer, this has to be selected. Yes or no? So I have to write C in bar there. Okay. Similarly, if you see, it will be C in bar here and C in. Okay. If you look the path. This, after finding the path, the same way if you go back and see in your original implementation, it is the same. It is in the first two, it will be C in and C in bar. Next one, it is C in bar and C in. Yes or no? That is the same thing. If we are checking and writing also, we get it. Yeah, we get it the same way. Got it? C in bar. So whatever was your I0 comes here, I1 comes here, I2 will come here, and I3 will come here. When I'm splitting it up into two smaller ones, this is actually the flow that happens. Okay. Okay. Now I'm stopping here. We have a little more to cover that I'll cover tomorrow. Okay. So now coming to our exam discussion. So let me first switch off the recording. Sweet revenge. Those who are online, please stay in the meeting. Okay, I will stop recording.